This is our PID Controller Trainer analog circuit based. This unit consists of signal source, controller and process. In signal source we have provided DC voltage variation from 0 to 12 volts, and at square wave we have provided from 0 to 2 volts with variable frequency and amplitude, and triangle we have provided for variable frequency. Okay, and in the controller we have provided V-in terminal, feedback terminal and error voltage terminal, and proportional control variation from 0 to 20 with potentiometer with switch, and integral controller with variable provision for variable gain from 10 to 1000, and this D controller can vary the gain from 0 to 0.1, and individual switches we have provided for proportional, integral and derivative. If you want to conduct proportional alone, you can switch on this I and D, keep off, and for P plus I you have to switch on both P and I. For PID you have to switch it on all three, and it's output of PID controller. And again, this consists of process: first order system with RC component, second order with variable damping factor by varying the resistance, and time constant with 10 milliseconds, and one integrator we have provided with 180-degree phase shift, and one inverting amplifier. To start with the experiment, connect the DC to V in and output to first order process, and first order process output to V out, VF. Now we can set the voltage to 2 volts by varying amplitude potentiometer DC, and now you can measure the voltage at VE and VF. VE, now the gain you can, now gain is 1, 0 corresponds to 5.5, so this corresponds to 1, gain 1. Now that output error can be calculated using Vs divided by 1 plus G. Vs is 2 volts divided by 1 plus G. 1 plus G, gain is 1, and what G gain is 1, and G, and set voltage is 2 volts. 2 plus 1 divided by 2 volts divided 2 divided by 1 plus G. 1 plus 1, 1, so we get 1 volts at error voltage, and feedback voltage also you can note down almost equal to 1 volts, so error voltage is 1 volts. Now we can set the gain to 2, so now it is 1 corresponds to 0, means 10 ohm. Now 1 Vs is 2 volts, 2 divided by 1 plus G, 2 divided by 1 plus G means 3, so output is 0.67, error voltage is 67 volts, and feedback voltage is 1.3. so if you go on increasing the gain, that error voltage decreases, that we can observe. This is for proportional controller, and if you had DI controller PI, so output offset error voltage offset is 0, offset voltage is 0, so V in is 2 volts gain, and feedback voltage is 2 volts, so error is 0 for P plus I, and for P plus I plus D also there is no effect for D controller in DC input. Now you can repeat the same for second order system also. In second order system also you can observe the same effect. This is for proportional plus integral, and proportional plus integral plus derivative, and for integrator as the process you can get this, because you can get the negative voltage. So if you in between, if you had one add inverting amplifier, inverting amplifier input into amplifier connect to feedback output, so you get the error voltage at 0 even if you switch off I and D. So this for with integrator, it's proportional plus integrator as the process. And for square wave input, connect square wave to V in, V out to second order system input, second order system output to VF, and you can connect one channel of CRO to input, so other channel connected VF. You can avoid a ground pin of the CRO. Now you can set the voltage to square wave amplitude to maximum. Now this is input and this is VF. You can observe the waveform at feedback terminal. This feedback terminal output. Now you can see the damping. Now you can set the damping factor at the market point, say 0.3, like that. If you increase it is going to maximum, so you have to keep the around 0.3 damping factor. This for proportional. If you increase the, now gain is minimum. At minimum gain, error is more, oscillations are less. If you go on increasing the gain, oscillations more, but error decreases, but never reaches equal to this input. So if you had P plus I, now you can see that offset error is 0, but still oscillations you can find. So if you increase the integral gain, error is still more, increases. So if you had D gain, that oscillations are minimizes. Now we can observe, suppose if you increase this, error is 0, offset error is 0, and also there were no oscillations. This is for PID controller with second order system. And if you same repeat for time constant, you can, this is for P, I, is for P, I and PID. So P plus I, P plus I plus D. In proportional control alone, you can get error, more error at minimum duty cycle, minimum gain, and maximum error. Error is minimum at high gain, but oscillations are more. If you add PI, so error minimizes, and if you add D gain, PID, so oscillations as well as error becomes 0. So this for time constant. And if you want to